Okay, so from Hexa-X-II side here, together with my colleagues Cristóbal and Christina from the Hexa-X-II project, our vision on the use case KPIs and KVIs. First of all, I want to start with the methodology here. In Hexa-X-II, we come from if you come from the use case side, so we identified use case families, 6 in total, as you can see here on the screen. And for each use case family, we defined a representative use case. It should be then representing us as a name, this use case family. Our use cases are around, and that's important to keep in mind, sustainability. But sustainability for us, it's a 3-pillar thing. So it's on environmental sustainability, social sustainability, and economic sustainability. So now, if you come from the use case, so here we have so far done work on the use case analysis, business model and stakeholder analysis, and preparedness for 6G. That's a kind of check if we can meet our social sustainability requirements and what to do if not. And the whole work of that will, and that's ongoing, be integrated in, we apply this as the KVI process methodology coming from the SNVC working group from 6G. So that's currently ongoing, and we will see how this fits all together. So from the use case side, for sure, we need the description, the problems to solve, but also we're on 6G, so why do we need 6G here? And we have key performance and the technical requirements, key performance indicator. That's kind of usual business. But on the other side, this duality, here we have the key values. So key values coming then, bringing in here the sustainability analysis. On the 3 pillars, that's important: environmental, social, and economic sustainability. And we distinguish here as well the footprints and the handprints. The footprint is kind of cost that you have to deal with. The footprint, you have to level it down, let's say, and the handprints, these are the benefits that you want to increase. Together with the use case comes for sure then the business model and stakeholder analysis. So that's how do companies create, capture, and deliver the value. Not to go into details, but just to say this ecosystem business model analysis includes and comes then for the use case to a stakeholder analysis, and always represented in an ecosystem pie chart. So that's the method we apply here in Hexa-X-II. And the preparedness for 6G, that's the objective here. That is, we have to analyze the challenges and risks which may counteract that sustainability targets are reached. So we need to identify and apply as well mitigation strategies. So if you have a representative use case and you did the sustainability analysis and the business model and stakeholder analysis, so then you come to challenges, and challenges then can be mapped to one or several risks, and these risks for sure then you can map it to one or several strategies to mitigate this risk, and the intention is then that the mitigation strategies have to be applied. And this comes then back to the stakeholders, how they apply these mitigation strategies. And that's then reiterating, because this for sure will be feedback and impact business models and the stakeholder analysis. So that's the methodology here we apply. And I said in the beginning, so we have currently work ongoing on applying the 6G IA SNVC KVI process. So that's the whole process, and we will fit in our work, and we apply this, and we try to fine-tune this process. So that's what we do here. So now I hand over here to my colleague Cristóbal, and we will just here provide an example of cooperating mobile robots use case.
Sure. So hello. So as Stefan showed in a few slides back, we delivered 20 use cases, which were grouped into 6 families. Then for each, we chose one use case that best represented the key aspects of this family. And that's the one that was further analyzed and renamed as representative use case. So in this slide, a summary of one of these representative use cases is shown, which is cooperating mobile robots, part of the collaborative robots family. So in a nutshell, I'm not going into too much detail. As the name suggests, this use case portrays autonomous robots with the ability to move, sense their environment, and being able to cooperate with other machines, but as well with humans to perform a given task. So this way, it can enable a group of robots to perform tasks beyond their individual capabilities. So then we've described the main problems to be solved or main challenges. That's on the right-hand side of the slide. And this, apart from validating the use case and the technical requirements, can also signal on how and where this use case can help create value. And of course, this is a very first step. As the next step in the process, as Stefan mentioned, we've also performed a sustainability analysis, identified possible impacts, both positive and negative, in the environmental, social, and economical dimensions. Then we've described the technical requirements, so some of them local ad hoc connectivity, so benefiting from the possibility of robots communicating together directly, leading to the creation of subnetworks, then extremely reliable and low latency communications beyond what 5G can deliver, AI and ML, which is also pivotal to the autonomy of the robots, while sensing and positioning capabilities help both in the operation itself and building more efficient ML algorithms. Next slide, please. So then, thank you. So lastly, the main KPIs identified are in the table on the left and have also been mapped to the template provided on the right-hand side of this slide. So here, the most relevant ones are user experience data rate lower than 10 megabits per second for most scenarios, connection density that will allow or ensure fluid motion of the robots, mobility, since robots will be moving in and out of these subnetworks, so it will create significant handovers. We've listed end-to-end latency, service level reliability, positioning accuracy, sensing capabilities, AI, ML. So basically, as you can see, so far we've done an assessment on the KPIs and the technical background mostly, but we've also identified relevant areas for value exploration. So as Stefan mentioned, we're currently working on applying this methodology and iterating over it to extract KVIs, which is also important to mention that this will be done in a subset of this use case, as the values are highly dependent on a specific context. So related to KPIs, this is still a work in progress, and hopefully we'll have results soon. So Christina, over to you.
Okay, hello, I hope you can hear me. So yes, in continuation to what my colleagues have said, here we are looking the KVIs from the system box designed for Hexa-X-II project. So just to give you a brief overview on how the system box work in this project, the system box are designed in an incremental manner to introduce new features as the project progresses. The use case that is chosen to be studied is the collaborative mobile robots use case, as it was just mentioned by Cristóbal, and it is mainly used for the scenario that is studied is for cobot-powered warehouse operations towards inventory management. So new enablers are to be introduced first in the first POC, which has now concluded, where management and orchestration enablers. On the second POC, which is now being studied, is pervasive technologies and network functions to be included, such as exposure of beyond communications data, such as sensing. And last, in the third POC is to have 60 device components, radio aspects, intent-based network aspects, etc. So as these enablers are being introduced, new key values are come up that need to be studied and addressed. And like previously was mentioned, they are categorized in 3 pillars: social, environmental, and economic aspects. So as the project progresses, new key values, KVIs are being introduced. And for example, let's say on top of the trustworthiness, energy, and financial aspects that are being considered in System POC A, in System POC B,
we need to
we'll have
wrap it up now. So
yeah, just give me 30 seconds. How to securely, let's say, for example, secure the data that are being exposed. So based on these, the KPIs that are identified for System POC A are, for example, power consumption and energy consumption are related to the environmental aspects. Our execution time is related to environmental and economical related key values. And last, the trustworthiness is a quantified metric related to social sustainability. Okay, so thank you.
thank you very much.
I conclude.
Yeah. So in the interest of time, we have very many presentations. Any questions you need to take offline or in the last session. So we need to move on to the next presentation. So thank you very much for that presentation. The next one is from Origami by Marco Gramaglia.
Hello. So I'm going to share my presentation. So hopefully you can see it, right?
Yes.
Okay. So
Presentation mode?
it's presentation mode?
No.
Now?
I still see it normal mode.
Okay. Let me do this way then. Sorry. Okay. So now I'm sharing my entire screen. Now?
Yes.
Okay. So sorry for this inconvenience. So I'm Marco Gramaglia, work package 2 leader for the Origami project. This is a Stream B project that just started last January. And yes, basically we are participating in this workshop, co-organizing it with the idea of exchanging our view on what are the KPIs that we are going to measure, the target values that we are trying to achieve, and then some initial discussion on the KVI framework, which for us is a bit hard to tackle. So we hope to learn and exchange with you on this topic. So let's start with the first part, enabling technologies and KPIs. So basically, in a nutshell, Origami aims to bring down 8 barriers that are currently making difficult the design and the transition towards 6G. So basically, through a state-of-the-art analysis, we identify these 8 barriers that span very different domains, ranging from the radio access network up to the exposure of data towards service provider and other operators. So we understand that those state-of-the-art barriers should be brought down. So we are doing that by enabling compelling use cases that we have defined that leverage on mostly 2 enabling technologies listed here. The first one is called network intelligence, NI. which is basically the application of AI/ML solution deep into the network architecture, including the edge and the far edge, so the radio. So through the application of this AI/ML solution, we're going to see how these barriers could be removed, and then an easier transition towards CG can be applied. So for us, AI/ML is one of the fundamental enabler that will be used to achieve the project objective. Through this process, we are going to define new architectural elements. So currently, we identified 3 architectural elements that we are going to design, called ZTL, Zero Trust Layer, that is basically an extension of the exposure layer that we have between the operator and the service provider. CCL, Compute Continuum Layer, that is basically an extended version of the virtualization solution towards the cloud that we currently have nowadays. And then the GSBA, that is an extended version of the current SBA architecture that we have in the core, extended towards the radio and towards the management of the network function. So this is basically the ecosystem where we move. Network intelligence solution, so AI/ML solution applied to some compelling use case, and architectural elements that are enabling it. So this is more or less the scenario in a nutshell. And these are the technologies, the 8 barriers that we want to bring down as discussed in the previous slide. So the KPIs, I'm listing them here, barrier by barrier, and now I'm going to discuss them briefly. So the first technology is infrastructure awareness and hardware accelerator pooling, and here we are targeting KPIs related to network energy efficiency, CAPEX and OPEX reduction, service reliability. Another barrier we identify is the interoperability of RAN intelligent controllers. So different architectural framework may have different ideas on these elements. So also here through our solution, which more you can read in more details in the project deliverable, are targeting KPIs related to network energy efficiency, CAPEX and OPEX reduction, service reliability as well. The third one is the design of scalable solution for 6G complex network problems. So in 6G, we are expecting to have a much larger scale of problems such as routing or scheduling. So we need to solve them fast. So the solution we design are going to target network energy efficiency. And here, this is the first KPI which is basically going beyond the ones defined by the TMB, that is accuracy and maximum latency of machine learning. So one of the KPIs that we are measuring to validate our solution is basically the performance of the machine learning algorithm that we have. Then a solution targeting distributed and streamlined access to transport domain computing. So embedding NI deep into the switches, again, targeting peak data rate, but also KPI related to machine learning. Global operator model, so achieving a federation of operators exchanging data among them with CAPEX and OPEX reduction, control plane latency as target KPI. Decentralized identity model, so authenticate once and use the network everywhere. Here again, control plane latency. Intelligent anomaly detection, CAPEX and OPEX reduction, of course, because we can improve the network to avoid these anomalies, but also metrics related to the ML, and then the cloud native core that we are going to decide. Again, here we are targeting control plane efficiency, which is something that is beyond the current PMP view. So the target, basically here, you can find the list of KPI that we have, the description of KPI that we're going to achieve. So those are basically the ones that were listed in the previous slide, and then the target value. So as you can see here, we have quite ambitious target values for those. So especially regarding energy efficiency for the run, reliability with finite reliability, very high peak data rate in switches, even if they are performing machine learning inference. And then you can read here all the others. For us, all the KPIs are equally important because they are really needed for bringing down the barriers I was discussing before. And then very quickly, for the second part of my presentation on the KVI, I just have one slide here, actually, because as we can see here, our methodology is just started the design. So basically, we're going to have an identification of key values that are relevant to our project. So we are listing them here in a list, but I mean, this is just initial work. And then we are going to associate every key value in a dichotomy. So they could be either use case specific, so from the algorithm, or architectural, so attached to an enabling effect of one of our architectural model. So after that, we are going to define and conceptualize KVIs, at least one per KV, ideally more, and try to target basically the metric that we can use to measure the indicator. So specifying the goal of the objectives, such as improvements or increase and decrease. So you can see here a list, a possible example of how we are going to use this framework. So KV trustworthiness, and then we measure it through the reliability and energy efficiency. This is very initial work, so we hope that after this workshop, we can have a clear idea on how to proceed. So that's all for origami. And
thank you very much, Marco. So well on time, on 10 minutes.
Okay.
Any questions you can take in the final session? So let's move on to the next presentation from the privateer, and Maria.
Hi. Yes. Hi, Patrick. Hi, everyone. Give me a moment to share my screen. Okay. Okay. I think that probably you don't see the presenter. You don't see.
No, we just see.
Just fix the slideshow. Yes. Is it okay now? Okay, probably now it is.
That's good.
Okay, perfect. Give me a moment also to clear the screen. Okay. So hi everyone. My name is Maria Christopoulou. I'm technical manager for the privateer project. And today I'm going to talk about some essential KPIs that can help us evaluate the performance, security, privacy, and trustworthiness in foreseen 6G networks. Today we are going to cover some categories such as AI-based intrusion detection, privacy preservation of machine learning models, adversarial protection, data anonymization, orchestration, and distributed ledger. Before we begin the presentation on the KPIs, some background on the project. So Privateer is a security project. and its objective is to design and develop security enablers for 6G networks by following privacy by design approach. It's the TRL is 4 to 5, and essentially we're targeting an integrated privateer framework that is going to be tested and evaluated in a 5G campus testbed against different use case scenarios. Now, the technical pillars of privateer include AI-driven security analytics populated with explainability and federated learning schemes. Next, we have security service orchestration, which is being populated with privacy awareness. We also focus on attestation, essentially remote attestation of infrastructure and services. And finally, we also introduce some cyber threat intelligence mechanisms that are based on searchable encryption in order to preserve the privacy of stakeholders in a 6G environment. Essentially, what we have in mind as stakeholders, we include the end users, we include the infrastructure providers, the mobile network operators, and the service providers. Now, this is the architecture, the high-level architecture. Essentially, you can see the technical pillars as they are mapped into the different horizontal layers. So you can see some of these pillars there, the adversarial training, for example, the federated learning scheme, the attestation components on the bottom of the picture. And essentially, these pillars are the basis also for the KPIs that we suggested in the first deliverable of the project, which was published about a year ago, deliverable 2.1. You can also check the Zenodo link here. Essentially, in that deliverable, the privateer consortium partners, they have provided a list of KPIs and KVIs, also as part of the SNS program. And then you can find relevant references, as well as some indicative values from the literature. But a disclaimer about these values is that they really depend on the specific use case and also on the system requirements. So in this presentation, I have included a subset of these KPIs to respect also the space and time limits that we have. And also we are working on releasing a white paper on 6G security and privacy KPIs and KVIs as, let's say, an updated version of what we have in deliverable 2.1. So I'm proceeding with the KPIs. The first category, let's say, we have termed it as AI-based intrusion detection because we are focusing on artificial intelligence for intrusion detection. In this case, we have the number of false positives and negatives as a KPI. Essentially, it's the percentage of incorrect threat identifications by the AI-based detection system. Additionally, we also have the mean time to detect a threat. It's the average time the system needs to detect a security threat. This also depends on the kind of threat that we're discussing. If it's an APT, for example. And finally, since we are focusing on federated learning schemes, we have also defined the accuracy loss, which signifies the decrease in accuracy of the federated model compared to a centralized model, which is calculated with the formula that you can see on the screen. Now, the next category is on privacy preservation of machine learning model and adversarial protection. Some context background before I proceed with the KPIs. Essentially, this involves the use of differential privacy, which is a technique that is used to ensure that when information is released, it doesn't compromise the privacy of individuals in the data. Now, this works by adding a certain amount of random noise to the data, which makes it difficult to identify any single individual's information. There are two parameters in differential privacy. One is epsilon, which measures how much noise we add to the dataset. And the second one is the delta, which is the probability that the privacy guarantee may not hold. Essentially, it's the chance that someone's data could still be guessed from the modified dataset. So since we add noise to protect privacy, naturally this leads to a decrease in the accuracy, let's say, of the data. That's why you can see here the accuracy loss in our KPIs. And after this, what I also would like to say is that another fundamental aspect of privacy in machine learning is protecting the individuals whose data was used to train the model. So one common type of attack that we need to protect against is the so-called membership inference attack. And this attack involves, for example, determining whether a specific individual's data was part of the model's training dataset. And an attacker might use this information to infer sensitive details, such as, for example, whether a patient's medical records were used in a model related to a particular disease, which is a privacy breach. And we evaluate the success of membership inference attacks by examining the attacker's ability to identify training records using precision and recall metrics. For example, precision is the fraction of records inferred as members of the training dataset that are indeed members. The recall measures the fraction of the training records that the attacker can correctly infer as members. So, taking all into account, we have come up with some KPIs regarding this. In the deliverable, you can also find some additional attacks. One is, for example, the model inversion attacks, where attackers attempt to infer properties of the training data, and reconstruction attacks, where attackers attempt when they try to reconstruct, let's say, the original training data samples. Here I have only included the inference of membership. So, for example, the accuracy loss that you see here for the private model, this has to do with the decrease in accuracy when you use privacy mechanisms versus when you are not using such privacy mechanisms, and it has to do with the privacy versus accuracy trade-off. We also have the performance loss and overhead when we are introducing adversarial protection mechanisms that where we can use the typical metrics, accuracy, precision, recall, and F1 score. And finally, we also suggested a model poisoning related KPI, which has to do with the percentage of adversarial agents that the system can tolerate without significant performance degradation. The next category has to do with data anonymization, and we are focusing on quality loss, which is really data type dependent and essentially signifies how much quality is lost when you are reporting the anonymized data instead of the real data. And essentially, these first categories of KPIs were mostly related to the AI-based security analytics, let's say, umbrella. We also have some KPIs for orchestration, time to repair. If you detect an anomaly breach, then how much time it takes to address this threat, how much time it takes to prepare the resources against different domains, and also the decision time in case you are using some kind of a reinforcement learning agent. It signifies how fast the machine learning model can actually process the data, analyze the network state, and make the decision to protect the network. Also some KPIs.
Wrapping up.
Okay. Essentially, these are the last ones. On the distributed ledger, there is some discussion about including distributed ledger and SIG-III. So distributed ledger has latency and throughput as some KPIs that essentially show the time between the receipt of request and the commitment of the transaction. So we can use latency and throughput, for example, to see, to assess, for example, whether some mechanisms affect our system. And finally, the trustworthiness, the KVI. Essentially, we are tackling trustworthiness through the level of trust, which is a challenging area, and Privateer is working on the level of trust definition. And also, we are using the levels of assurance from ETSI that has to do with whether you have integrity verification mechanisms in your system or not. And this is up from my side. If you have any questions, please let me know.
Thank you, Maria.
Thank you very much.
As mentioned earlier, any questions you can take in the chat or in the last session.
Okay, thank you.
Thank you. So moving on to the next presentation, it's from Deterministic 6G with Oliver Hoeftberger. Cannot hear you, Oliver. No, still not. No, still no audio. Cannot hear you. Should we try another order of the presentations while Oliver fixes his audio? Is that okay, Oliver? Some visual. So if we can go to the next presentation from Safe 6G with Garcia, Sanches, or Alvaro, Andrés, Anaya, Amariles. Are you ready to present?
Yes, we are here.
Yeah, so let's take you first.
Okay, let me present my screen. Second. So, can you see my screen?
No, not yet. For me, it's still Maria's.
Yeah, I also still see my screen, although I have stopped sharing my screen, and I'm only through my mobile phone now. I don't have the presentation open.
No, it seems I'm not presenting. Okay. Can you see it now?
Can see your desktop.
Okay,
That's good.
it's good now. Okay, hello, this is Daniel Garcia from Telefonica. We are leading KPI and KVI definition task in Safe 6G project. First of all, I would like to set the context of Safe 6G task, which has recently started. So we are at an early stage in our work yet, and most of the technology pieces are still under definition. Okay, where are we now? For the time being, we have been reviewing and analyzing the documents proposed by TMB working group related to KPIs, definition and measurement tools, proposed to evaluate them. A spreadsheet condensing all the KPIs defining by the ICT projects participating in the working group has been created. So everyone in Safe 6G can review them and set it as reference when selecting KPIs for their technology, and quickly realize if the target value proposed in the standards is suitable or it's required to define a new one for the scope of our work, as it has been defined by other ICT projects. This has also been useful to detecting which areas it is likely Safe 6G can contribute, since we have not seen many KPI definition on fields like AI, MLOps, or cybersecurity, which are the core parts of the process we'll see later. For KPI definition, we have done the same, but with the documentation released by Vision and Societal Challenges Working Group. The same methodology shared by the working group has been proposed in Safe 6G KVI definition. I will briefly present in a while the contribution we target in our project, at least what has been identified so far. Okay. Besides, templates for both KPI and KVI definition have been extracted from the documentation analyzed, and we will use the same fields and structure to call new ones, new KPIs, or the specific ones we are currently missing from our technology. Okay, very quickly, a glance on Safe6G main technologies. The main objective of the project is to create 5 new mobile network functions focused on 5 pillars: security, safety, privacy, reliability, and resilience. So we consider cybersecurity is the main KPI we will contribute from the project, as well as AI and MLOps, which is also an important pillar of Safe6G. Apart from it, we will have to define as well new KPIs for artificial intelligence and MLOps areas, blockchain specific ones. It's also part of the technology we will leverage to create the network function, and augmented reality related KPIs are also part of the project, because we are creating use cases to validate the technology that we are developing in the project. For sure, we will also validate other technologies like 5G, 6G, but we think the KPIs which are already defined in TMB will suffice. Okay, we broken down the technologies that we are using and leveraging in Safe6G project. As I've said, the summary will be the same. We are targeting to contribute in cybersecurity, AI, and MLOps mainly. Okay, regarding KVIs, we have a long way to walk yet, but there is one of them which is clearly, or which will be clearly a core KVI of Safe6G framework, which is level of trust. It is a KPI which aims to measure the level of trustworthiness the network can provide to a user, and the other way around as well. The user can demand a specific score of trustworthiness, I would say. Level of trust is intrinsically linked to the performance of the 5 core functions of the Safe6G framework, which are the same as the pillars I've said: safety, security, privacy, resilience, and reliability. These functions are coordinated using explainable AI and ML techniques to ensure a user-centric approach to trustworthiness in 6G networks. As we explained here, level of trust is a dynamic KPI which depends on several KPIs, which are evaluated from Safe6G functions and are adapted to the evolving needs and trust specification of the network's user. The idea is initially the user will demand some features, will demand some user intents, let's say, and we will infer a level of an initial level of trust, which will be passed to the network functions, and then the network functions will evaluate different KPIs which are related to the level of trust, and hence we will apply these KPI targets. So it's a relevant goal we will be tackling in the following months, defining the list of KPIs which are tightly bound to each one of the functions and the overall level of trust the Safe6G function can provide. That's it from Safe6G side. I've been quick, I think.
Thank you very much. Yes, now we caught up a bit with the agenda. So as previously, if there's any questions, let's take them in the final session. Check with Oliver again. Have you managed to fix your audio?
Can you hear me now?
Yes, now I can hear you.
Great. Why this did not work with this headset? I'm trying to share my screen. Should be visible now.
Yes, that's it.
Great. Hi again, I'm Oliver Hoeftberger from P&R industrial automation. We are mainly representing the use case side in the deterministic 6G project, which I'm going to present some insights the next couple of minutes. The objective of the project is to develop a new architectural building blocks that should optimize the end-to-end deterministic and dependable communication, such that we can enable use cases in the industrial domain or in other domains as well. I'm going to that in a few seconds. The main pillars of the project are the definition of those architectural aspects that relate to end-to-end deterministic communication. This is, of course, security. We are including edge cloud computing as deterministic services. We need to include TSN network, DetNet networking as well, together with the 6G wireless communication. Then there is a focus on awareness of the current situation. This is mainly targeting at the network level, but also on the application level with digital twins, for instance, and then the anticipation of the situation and control of situations before certain bad situations would happen. The use cases, I'm putting here only a couple of them. We do have 4 different use case domains analyzed with many different use case scenarios. One of them is adaptive manufacturing, which is very demanding in the way that we are looking into a very flexible future, very customer-centric production, which means that we also need a lot of flexibility in the production, and this means that also flexibility in the communication is needed. In the production, we of course will need many mobile components, like the automated vehicles for transporting, but also for production. And what's really important in these use cases is to really close the control loops over the wireless network, which is quite challenging. Another factor is the deeper integration of humans in the production to really interact with machines. This is often a question of safety, and here we need the real-time control loops included in the safety mechanisms of those systems. One concrete use case, or one part of the use case, could be, for instance, the usage of exoskeletons in the industrial context. Here we see the demand for offloading the control of those exoskeletons. So basically, the exoskeleton can be used then to assist people, humans, in their working process. The system, however, should not be static with the assistance it provides, but to really adjust the amount of assistance and to the current task and the current situation. This needs a lot of adaptability in communication. It needs a stable communication with the surrounding system in order to prevent any harm and injuries of the people wearing those devices. The technology we are after in the project are basically data-driven analysis of the wireless 6G system in order to predict different stochastic parameters of the system using AI and ML technologies. Based on that, digital twins of the network, but also the application can be created that may be used for scheduling and planning algorithms in order to optimize the production systems. And based on that predictions, we try to find methodologies to mitigate different, or the influence of stochastic elements in the 6G system, for instance, in a way that we can react proactively such that the application can adapt to possible situations in order to remain within the defined bounds of the application and to guarantee certain KPIs in the system. Part of it is to create new wireless-friendly standards. TSN and TETNET standards are currently created, and TSN is already well known. However, we need some evolution of those standards as well in order to make the typical stochastic properties also aware in the wireless, the wide domains. Inclusion of edge computing in the end-to-end scheduling is an important topic. Of course, security, time awareness, using fault-tolerant time synchronization over the 6G network. At the end, we will come up with a service description that is really focusing on dependable service provisioning in the communication and computation sense. Based on the service description, the robust scheduling mechanisms which are developed in the project should be applicable, and this should enable the application to dynamically react to changes in the system, in the environment, in signaling strength, for instance, and so on, and to allow the dynamicity, the flexibility of those future systems. Of course, based on that, the KPIs that we are working on are mainly focusing on the latency. Many of them are application dependent, so I've just been mentioning here a couple of them. Since we are not really working to optimize the KPIs of the 6G system itself, but we want to cope with the situation we find in such systems rather than improving the 6G technologies. We need to find means to live with the situation that we find. So we are trying to identify application KPIs that the applications need, and then we need to define means how to specify the services that are needed in a way that the control system can automatically decide which applications can be operated at which level. So actually we could define then different service levels, and each application could then be optimized to the achievable service level that the system can provide in the current situation. Based on that, we do already see a couple of KPIs like packet delay or latency, packet delay variations, or jitter. They can be found in many projects, I would say. We do have a strong focus on the dependability, so packet loss, timely delivery rate, but also mean time to failure. We try to optimize schedulability. So this means if I do have a lot of flexibility and a lot of application demands for dependable communication, we also need to be able to schedule that communication in the system, and we need to predict the behavior of the system. Other KPIs go into the direction of capacity to guarantee the bandwidth and to really ensure that the bandwidth can be delivered to the different applications. And at the service level,
Oliver, if you can wrap up now.
Yeah, just half a minute. There we find the KPIs of end-to-end service latency, reliability, and availability. We also use the same methodology for the KVIs as we have heard in the previous talks. That is based on 6GIA guidelines. Here we mainly see the enabler technologies for KVs that can be provided by the application. We are not really working on optimizing those KVs and KVIs. But we have been looking at certain KVIs in the domains of environmental impact areas and also socioeconomic impact areas based on the existing use cases. But what we would like to see is if we can bring those KVIs directly into the service description in a way that the system could automatically work and optimize the KVIs in flexible systems of the future. One example could be, and this is the last slide, in the exoskeleton use case, there is, of course, the health improvement, the health protection of people in factory environments, for instance. And here we could define the reduction of healthcare costs or the number of injuries in such situations as the KPIs that could be automatically optimized by the system. Thank you for listening.
Thank you very much, Oliver. So as earlier, any questions in the final session or in the chat? So moving on to the next presentation from 6G Tandem.
Yes, that's me. Do you hear me?
Yes.
Great. I will share my screen. Do you see my slides?
Yes, if you go
Not
to
in
presentation
the-
mode.
Not in the slideshow. No?
No, yes.
Perfect. So my name is Aghdam, and I am technical lead of 6G Tandem. And today I will present about the KPI, KVI, and a bit on use cases. It's a Streambeat project, and maybe I can show you what the project is all about. So here is a picture of the system vision that we have for 6G Tandem, and I will go quickly through some topology and terminology, what I'm talking about here. So we have mainly envisioned to have 6G Tandem deployed in indoor scenarios. Of course, it doesn't hurt to move to outdoor, but in this project, we have mainly focused on indoor, and I will explain why. And so 6G Tandem, the tandem word comes from the dual frequency operation, and here we envision that you can make use of the low frequency sub 10 gigahertz products, let's say Ericsson radio dot working at 3.5 gigahertz, and those are the blue boxes, access points. And then we have this central tandem unit distributing the sub-terahertz, in our case D band, 140 to 170 gigahertz signal towards these fibers and towards these small boxes, baseband unit we have, or radio unit, booster unit and radio unit, and the white ones are inactive. And we have the UEs, which should have a possibility to connect with both. And so in tandem, it is not just the hardware. We are a consortium working both on the system and hardware. So we are co-designing the hardware and system together for this dual band deployment. The tandem operation opens up new possibilities for end-to-end services. And for example, the software user plane, the software will be used for the user plane, offering high performance, high throughput, low latency services, and the sub-10 will be the control plane. This is the scenario we are investigating, among others. And sub-10 would be enabling the smooth and reliable operation. So speaking of enabling technologies in 6G tandem, as I have previously mentioned, so we target very high bandwidth over the sub-terahertz link to provide throughput and enable high accuracy positioning. That's one of the services we are also investigating. And then using the fibers, and you should mind this, that it is not really the optical fiber, it is analog signals over fiber. And the fiber is a plastic microwave fiber. It's like a dielectric waveguide, essentially. So they are very tiny, lightweight, and inexpensive. So which enables us to have dense multi-user capacity. And at the end of the day, we also have the dual frequency operation, which enables this usage of these two advantages of these two frequency bands. So about the KVIs, essentially through the use cases that we have investigated, we mainly have focused on the socioeconomic aspects and of course lowering KPIs and OPEX. And why do we think that we are lowering the expenses? Is because the radio stripe is a flexible type of deployment. It's light, low cost, and our transceivers will also be realized in silicon technology, so by CMOS, by Infineon. So, so the whole thing should be, inexpensive. And also that the flexibility it offers, you can mount these fibers on the walls and ceilings, and the fact that for sub-terahertz we have problems with the blockage, you can have the possibility to be closer to the users, and it gives you more degrees of freedom for the installation. Socioeconomic aspects, we have investigated the needs of society and industries, and mainly focusing on health, entertainment, and improved industrial processes. And our main input has been the ongoing or previous EU projects such as Hexa-X and Reindeer, as well as the latest 3GPP documents. So that they have been our references. So I thought maybe we can also discuss a bit here on or focus on the deployment scenarios that we have investigated, and it's been mainly 3 selected environments. We have focused on industrial sites, and when it comes to entertainment, we have the sport event arenas and public transportation hubs. And we have also done some link budget calculations because of this to understand the requirements on the hardware. So, for example, this is one of the scenarios. We have these industrial sites. On the other hand, we have the public transportation hubs and focusing on impact on society, affecting the way people commute, offering the future of smart, efficient, and sustainable urban transportation system. And the characteristic of this type of environment is that you have dense concentration of passengers, which can place a significant strain on the communication infrastructure. So that is another type of deployment, and you see that, not to mention, these violet ones are the fiber with the sub-terahertz transceivers, and then we have the these radio dot type of sub-10 access points. So yes, and we have also included this passenger's experience where they require reliable communication and public safety concerns. The third environment has been the, as I mentioned, sport arenas, and we have discussed the impact on society that you want to have smart and connected stadium market, which has become more and more interesting, and the characteristic is again dense concentration of spectators. And why this environment is interesting is that if you have IoT in smart stadiums and you have many spectators that are sharing and interacting high stream data rate, and in the future they will be using the AR, VR, XR head mount devices. Yeah, you have again stringent requirements on the communication infrastructure. And then coming up to the KPIs, these are the main KPIs that we have been focusing on: the capacity, latency, packet loss, and the localization. Of course, energy consumption is our, we have it, we are studying it on the horizon, looking at, okay, if you have this high frequency communication, okay, at the end of the day, you have to generate the signal and so on. So we are looking at the whole system to see how the energy consumption is looking like. But yeah, it's a bit yeah, not defined yet here. Yes, and I will jump on this one quickly. So we have the identified use cases, almost 16 use cases here, and we have sort of classified the in terms of the application: AR, VR, XR, URLLC, and positioning and tracking. And we have also some extra use cases, for example, using the sub-terahertz radio strut as a fronthaul solution for other access points. And so I haven't used this template for the KPIs, but I can only mention that across these 16 or 15 I have here use cases, we have sort of captured the highest traffic volume densities, and it sort of depends on mostly on the AR, VR, XR use cases where this, for example, video compression is sort of determining what you get at the end of the day. So this is not really written in stone, but anyway, that's what we have come up to, and the reliability more than 5 nines in automation in Industry 4. Yes, that was it. That was my presentation. Sorry.
Thank you very much.
Yeah.
Very interesting.
Thank you.
So in the interest of time, we need to move to the final presentation. We're a bit behind schedule. The final one is from Predict 6G by Marc, Mollà.
Yes, I hope you are seeing my screen.
Yes, and we can hear you.
Great. So my name is Marc Mollà from Ericsson, Spain. I'm here to present the Predict 6G project. This is a project that focuses on the end-to-end deterministic services that can span across network with different technologies and different administrative domains. According to our vision, we define determinism as using 3 concepts. The first one is the reliability, where we are trying to improve the reliability of the networks and try to guarantee that we deliver the communication services. Also, we are focusing on time sensitiveness, where we are trying to provide better performance in terms of latency, but not only by lowering the latency, but also by trying to bound the variation of the latency. And finally, our third pillar is the predictability, that we are trying to predict to forecast the behavior of the network, the real behavior, not the expected one. Okay. This is the architecture that we are defining. I'm not going to go through details, but basically, yeah, I want to highlight that we are working in the data planes of different technologies, and there we are trying to improve the both reliability and the time sensitiveness in each of the domains. And then we have a kind of control plane that is in charge of building the end-to-end services and try to implement the predictability of our services. Okay? For the KPIs, we publish in one of our deliverables the project KPIs, where basically we try to define to find a common definition of KPIs, not only in the project but also across the projects. And here I highlighted, I would say, the 6 KPIs that we will contribute more. Okay. The first family that we are working on is obviously the latency. And here we're working with service latency that is highly dependent on the application, not only because the application, each application has its own traffic model, but also because depending on the application, we will have 1, 2, 3, 4 journeys through wireless networks. So this is the reason that for service latency, we have a wide range of goal in the KPIs that depends on the number of time that we use the radio access. Okay? And also we focus on the jitter that we define as delay vibration, and this is probably where we can mostly contribute because we are working basically on layer 2 of the network. Okay? And our target here is to reduce the variation of the latency to a value lower than 1 millisecond. In the second family that we're working on is in the reliability in the packet lost. Okay, so basically we use the packet loss KPIs, pretty standard definition, but here due to our particularity, we also, depending on the application, we also include as packet loss all the packets that doesn't arrive in time. Okay, and we introduce a new KPIs that is the packet ordering, mainly because in our use cases comes from the industrial verticals and they are used to delegate the ordering of the communication to the network. And here we put the KPI in order to measure, not only to measure the ordering that we provide in our solutions, but also because it introduces some restriction of the technology that we can use. For example, we cannot aggregate different ways that have different performance because then we introduce a disorder in the communication. And finally, we also work in the service, reliability and availability. Again, we use pretty standard definition of both of the KPIs, but in this case, we also introduce the concept of defined SLA, meaning that if a network is available but is not providing the KPIs, the target KPIs that we define it, so for us it's not continuous. Okay. Regarding KVIs, we are working basically in 2 sets of KVIs. One is in the business value, that our improvements can provide. And we have an ongoing activity that is analyzing these business impacts and migration guidelines toward these 6G scenarios that we are working on. And also we have a track working in the security, not only in the security in the data plane, but also in the security between the federation of the domains, as we are working with different domains, with different administrative domains, let's say. Okay. So to wrap up, if you don't want to read about our boring deliverables, we produce some demonstration of the working that we are doing. So we have in the lab we have a demonstration, a smart factory using a real 5G network, and on top of that we built some time-aware schedulers. And here we demonstrate that we can reduce the variation of the latency to less than 1 millisecond. And in the other demonstration, we have been working on coordinating the target awake time with some time-aware schedulers defined by the IEEE. Okay. And that's just for my side. I try to speed up.
Thank you very much. So we're almost back on track. This concludes the second session with the presentations from the Stream B